quantum breakthrough, shrinking particle accelerators onto a silicon chip. A revolutionary advancement in quantum physics may soon allow us to condense massive particle accelerators onto a tiny silicon chip. Scientists are delving into the mysteries of the universe using minuscule particles known as plasmons. These unique particles enable researchers to trap potent electromagnetic energy in areas smaller than a grain of sand. This groundbreaking discovery has the potential to transform various fields, including physics and medicine. Harnessing the power of plasmons. Central to this exciting development are a special class of plasmons referred to as extreme plasmons. Unlike standard plasmons, which exhibit gentle, minor vibrations of electrons, extreme plasmons oscillate with remarkable intensity. Their movements approach the physical limits of electron dynamics, generating extraordinary electromagnetic fields that reach petavolt per meter, PV per meter, levels far exceeding any previous laboratory achievements. Until recently, controlling these intense plasmons posed a significant challenge for scientists. However, Assistant Professor Akash Sahai from the University of Colorado, Denver, has discovered a method to manage them in a safe and predictable manner. By employing a newly formulated quantum kinetic model, Sahai and his team have successfully characterized the behavior of these extreme plasmons at minuscule scales. Their research, prominently published in the journal Advanced Quantum Technologies, could revolutionize experimental physics. This is incredibly exciting because this technology will pave the way for entirely new areas of research and have a tangible impact on the world, Sahai expressed. Historically, we've experienced technological breakthroughs that have propelled us forward, such as the discovery of subatomic structures leading to lasers, computer chips, and LEDs. This innovation, rooted in material science, aligns with those advancements. Understanding the mechanism, extreme fields on a compact chip. Currently, scientists investigating powerful electromagnetic fields rely on large and expensive particle accelerators. Facilities like CERN's Large Hadron Collider extend nearly 17 miles underground, accelerating particles to extreme velocities to uncover fundamental particles or elusive dark matter. Sahai's discovery could soon enable these colossal machines to be miniaturized onto a silicon chip smaller than a thumb. Tiny Particle Accelerator is millions of times smaller than CERN's Large Hadron Collider. New nickel-tungsten alloy powers greener, faster memory chips. Breakthrough MRAM chips deliver faster, ultra-efficient computer memory. Sahai's innovative approach utilizes a specialized silicon-based material capable of enduring the intense energy produced by high-speed particle beams. As these beams traverse the material, electrons vibrate energetically in a collective wave known as a surface crunching plasmon. This highly energetic plasmon compresses electron waves into remarkably small regions, merely a few tens of nanometers wide. Sahai's quantum kinetic model, grounded in advanced physics principles, accurately predicts the movement of these electrons and the energy they generate. The ability to manipulate such high energy flow while maintaining the material's structural integrity is the true breakthrough, explained Kalyan Tirumalasetti, a graduate student collaborating closely with Sahai. This technological advancement has the potential to create a significant impact on the world. It revolves around comprehending how nature operates and leveraging that understanding for positive change. From gamma-ray lasers to multiverse theories, the potential applications of this breakthrough are virtually limitless. One particularly exciting prospect involves gamma-ray lasers, devices that have previously existed only in the realm of science fiction. Unlike conventional lasers, gamma-ray lasers could specifically target and destroy cancer cells without damaging healthy tissue. They could also enable doctors to observe cellular activity at the atomic nucleus level, significantly enhancing our understanding of diseases and their treatments. Gamma-ray lasers could soon become a reality, Sahai remarked. We could achieve imaging of tissues not just down to the nucleus of cells, but even to the nucleus of the underlying atoms. Ultimately, we could develop gamma-ray lasers capable of modifying atomic nuclei and eradicating cancer cells at the nanoscale. Beyond medical applications, extreme plasmons may also provide answers to fundamental questions about the universe. By recreating conditions that were previously only achievable with massive particle accelerators, scientists could explore theories related to dark matter, vacuum polarization, and even the existence of multiverses. This capability could either validate or challenge groundbreaking theories proposed by renowned physicists like Stephen Hawking. For Tirumalai, these possibilities are profoundly inspiring. Exploring nature and understanding its fundamental workings is incredibly important to me, he shared. However, engineers equip scientists with the tools to achieve more than mere understanding. That is truly exhilarating. What lies ahead for quantum technology? At present, the researchers are fine-tuning their silicon chip design at the SLAC National Accelerator Laboratory, which is operated by Stanford University. They are diligently working to translate their theoretical models into practical devices. Although real-world applications may still be years away, Sahai remains hopeful that his work will be widely utilized within his lifetime. CU Denver has already obtained provisional patents for this technology, both domestically and internationally. As they continue their testing, Sahai and Tirumalai are committed to their work, driven by the immense promise their breakthrough holds. In the lab, we dedicate long hours because we believe in this, Tirumalai added. It's not merely about creating something impressive. It's about advancing science in ways that could genuinely matter. As this quantum leap unfolds, scientists around the globe are watching with keen interest. This tiny particle breakthrough could soon redefine our approach to studying the universe and ultimately transform our lives. Unleashing extreme electromagnetic fields in the lab, a quantum leap forward. Imagine being able to harness the power of extreme electromagnetic fields, previously only possible in massive facilities like the Large Hadron Collider at CERN, within the confines of a lab. This is exactly what Akash Sahai, an assistant professor of electrical engineering at the University of Colorado, Denver, has achieved. But here's where it gets groundbreaking. His innovation could potentially shrink massive colliders to a chip, revolutionizing the way scientists explore physics, chemistry, and medicine. Sahai's inspiration stems from the dire need for innovative tools to push the boundaries of scientific exploration. Existing techniques require building large facilities costing billions of dollars and are limited to small scientific communities. This threatens to severely limit the future generation of scientific explorations. Sahai's work is a game-changer, enabling scientists to explore new frontiers without the need for massive infrastructure. So how does it work? Sahai's innovation involves three key concepts: materials, a quantum gas, and lasers. The materials used in his research can withstand interactions with high-intensity particle beams due to unconventional heat transport owed to quantum effects. This is a significant breakthrough, as previous materials were considered one-shot or dispensable. The quantum gas, also known as a conduction electron gas, is present within all conductive media and occupies discrete quantum states. Sahai's work is the first to conceptualize and analyze non-perturbative excitations of this quantum gas, referred to as extreme plasmons. These plasmons can be excited within quantum materials by a particle beam, resulting in electromagnetic focusing fields that can oscillate the tail of the beam at incredibly short wavelengths. But here's the part that gets really interesting. When the ultra-dense quantum electron gas is non-perturbatively excited, the electrons compress into exceedingly small volumes, resulting in large electromagnetic energy density. This is measured as an electric field, which can be used to build machines needed for fundamental physics. Sahai's material manages the heat flow generated by the oscillation, keeping the sample intact and stable. Thanks to an emergent phenomenon underlying extreme plasmons, the potential applications of this technology are vast. Sahai says there are currently 3 decadal objectives: developing a new particle accelerator technology based on extreme plasmons to probe unknowns like dark matter and dark energy, demonstrating nanobunching or nanomodulation of ultra-intense electron beams for coherent gamma-ray production, and nanofocusing of the ultra-intense electron beam to drive polarization or opening of the vacuum. But what's the most surprising aspect of this work? According to Sahai, several well-established accelerator physicists initially thought this quantum tool was merely a theoretical exercise. However, when the researchers saw preliminary signatures indicating the veracity of their theoretical predictions, the feeling was beyond words. While the researchers have made significant breakthroughs, they still face numerous challenges. The current material samples are like the first transistors made at Bell Labs or the first chips made at Texas Instruments. To realize the full potential of this technology, custom-designed materials are needed, both in structures and microscopic properties. The researchers are currently seeking funding to improve their plasmonic chip build and its tunability. With further funding, they hope to build high-quality quantum materials to extract the exquisite details and scaling laws for the benefit of future generations and to revolutionize the reach of imminent scientific exploration. So what do you think? Can this technology really shrink massive colliders to a chip? Will it revolutionize the way scientists explore physics, chemistry, and medicine? Share your thoughts in the comments below. Unlocking the multiverse? New quantum tech breakthrough explained. Imagine a world where a gamma-ray laser could safely obliterate cancer cells, leaving healthy tissue untouched. This isn't just a pipe dream. It's a potential reality that's closer than you think. A groundbreaking discovery by a University of Colorado Denver engineer is paving the way for technologies that could revolutionize medicine, physics, and our understanding of the universe. But here's where it gets controversial. Could this technology also prove the existence of the multiverse? Assistant Professor Akash Sahai, Ph.D., from the Department of Electrical Engineering, has made a quantum-level breakthrough that could support the development of such cutting-edge possibilities. His work has garnered significant attention in the quantum science community for its potential to transform multiple fields. Sahai's discovery was even featured on the cover of the June issue of Advanced Quantum Technologies, a leading journal in quantum materials and research. This technology is incredibly exciting because it opens up entirely new fields of study and has the potential to directly impact the world, Sahai explained. Historically, we've had technological breakthroughs that have propelled us forward, such as the discovery of the subatomic structure leading to lasers, computer chips, and LEDs. This innovation, also rooted in material science, is along the same lines. So, how does it work? Sahai has developed a method for generating ultra-intense electromagnetic fields in a controlled lab setting, achieving strengths that were previously unattainable. These fields are created by the rapid oscillation and scattering of electrons within materials and are crucial for technologies ranging from microprocessors to powerful particle accelerators used in the search for dark matter. Traditionally, producing such strong fields has required massive, complex infrastructures. Take, for example, the Large Hadron Collider at CERN in Switzerland, which spans 16.7 miles and uses advanced radio frequency systems and superconducting magnets to propel high-energy beams. Operating facilities of this scale demand significant funding, extensive infrastructure, and carries inherent technical risks. To overcome these limitations, Sahai created a silicon-based chip-scale material that can withstand the impact of high-energy particle beams. This material efficiently channels the energy produced by the oscillating quantum electron gas and maintains structural stability by controlling the resulting heat. The rapid electron motion is what generates the electromagnetic fields. Sahai's innovation allows researchers to observe high-energy field behavior in a device no larger than a thumb, presenting a potential path to reduce the scale of massive accelerators to a compact chip-based format. Manipulating such high-energy flow while preserving the underlying structure of the material is the breakthrough, said Kalyan Tirumalassetti, a graduate student in Sahai's lab working on the project. This technological advancement can make a real change in the world. It's about understanding how nature works and using that knowledge to make a positive impact. The technology and method were designed at CU Denver and tested at SLAC National Accelerator Laboratory, a world-class facility operated by Stanford University and funded by the U.S. Department of Energy. Applications of this technology, CU Denver has already applied for and received provisional patents on the technology in the U.S. and internationally. While real-world, practical applications may be years away, the potential to better understand how the universe works and to thereby improve lives is what keeps Sahai and Tirumalassetti motivated to spend long hours in the lab and at SLAC. Gamma-ray lasers could become a reality, Sahai said. We could get imaging of tissue down to not just the nucleus of cells, but down to the nucleus of the underlying atoms. That means scientists and doctors would be able to see what's going on at the nuclear level, and that could accelerate our understanding of immense forces that dominate at such small scales while also leading to better medical treatments and cures. Eventually, we could develop gamma-ray lasers to modify the nucleus and remove cancer cells at the nano level. The extreme plasmon technique could also help test a wide range of theories about how our universe works, from the possibility of a multiverse to exploring the very fabric of our universe. These possibilities excite Tirumalassetti, who once thought of becoming a physicist. To explore nature and how it works at its fundamental scale, that's very important to me, he said. But engineers give scientists the tools to do more than understand, and that's exhilarating. Next up for the duo is a return to SLAC this summer to keep refining the silicon chip material and laser technique. Unlike in the movies, developing breakthrough technology can take decades. In fact, some of the foundational work that led to this pivotal moment began in 2018 when Sahai published his first research on antimatter accelerators. It's going to take a while, but within my lifetime, it is very probable, Sahai said. And this is the part most people miss. The potential implications of this technology go far beyond medical advancements. It could fundamentally alter our understanding of the universe and even prove the existence of the multiverse. But what if it doesn't? What if this technology leads us down a different path entirely? These are the questions that keep scientists up at night, and they're the same questions that make this field so exciting. Reference: Extreme Plasmons by Akash A. Sahai, 19 May 2025. Advanced Quantum Technologies. DOI 10002. Quote, 2025-0037. Never miss a breakthrough. Join the SciTech Daily newsletter. So what do you think? Could this technology revolutionize our understanding of the universe? Or is it all just a bunch of hype? Let us know your thoughts in the comments below. And remember, the future is always just around the corner. Sometimes it's just a matter of looking in the right place.